Welcome to the session, Everyday Objects as Interaction Surfaces. I will be your tour guide. My name is Mark Newman. I'm from the University of Michigan. We have 3 full papers and 2 notes. A lot of exciting work that will get you charged up after lunch. We also have an honorable mention and a best paper in this session, so a lot of exciting stuff. So without further ado, we will have our first presenter. He's going to be presenting the paper Touch Tokens, Guiding Touch Patterns with Passive Tokens. And our presenter is Rafael Morales Gonzalez.
Thank you for the presentation, and thank you everybody for coming. I will present Touch Token. It is a project I have been working on with Caroline Appert, Gilles Bell, and Emmanuel Petriga. Our goal was to offer a low-cost approach for building tangible interface. In our approach, we only rely on easy-to-make passive tokens that can be recognized on any tactile surface. Our system relies on a hypothesis that a given token will act as a physical guide to constrain a specific grasp. When the user are touching the token at the surface at the same time, we can recognize the specific relative spatial configuration of fingers that is associated with each token. We call this finger spatial configuration as a touch pattern. Before describing the detail of touch token, I will give a quick tour of existing approach for building tangible interface. First, some projects rely on diffuse illumination tabletops. These are tables that are equipped with camera below the screen, and that made it possible to implement computer vision algorithms to recognize both object and hands in contact with the surface. The main problem with this technology is that it requires a bit of equipment and is remain sensible to the environment such as lighting condition. Other projects rely on capacity surface. The principle of capacity screen is that they detect a drop in capacitance when one or more fingers touch them. Then building a tangible interface means fabricating conductive objects that will get detected by the surface when user touch them. But the main problem, the main difficulty with this approach is that it requires some knowledge in electronics to design conductive objects. It needs to establish a robust conductive circuit between the finger and the surface. Another interesting project is Touch Tool. Like our approach is relying on the idea of recognizing the grasp that is specific to a given physical object. But here there is no physical tool. They simply mimic how they hold the physical tools, and they use machine learning approach that require a lot of training. Our approach relies on a set of simple resources, a set of passive tokens that can be easily built with a laser cutter or 3D printer, a simple tactile surface like a tablet, and a multi-touch recognizer that we make publicly available for downloading. As I mentioned before, our recognizer analyzes the multi-touch pattern in order to identify what is the token that guides this specific touch pattern. The recognizer stores a library of template touch patterns that consists of one or more representative touch patterns for each token. When the user touches the screen with at least 3 fingers, our recognizer compares this touch pattern to all the patterns stored in the library and outputs the name of the template that is the closest to the input touch pattern. To compute what template is the closest, we run a best alignment algorithm that compares the input to each of the templates we have in the library. I will detail one example how this best alignment works to compute the distance between a template touch pattern and the input touch pattern. Computing the distance between 2 touch patterns is not straightforward, as touch patterns arrive in any order. Also, we want to be rotation independent in order to not force the user to hold the token with a specific orientation. So the recognizer first sorts the point in the template touch pattern in the counterclockwise order. It then rotates this template touch pattern in order to align the first point with the x-axis using the centroid as a reference. Then it does the same treatment to the input touch pattern. It first sorts touch points in the counterclockwise order. And as we have no guarantee that on the order in which point were captured by the tactile surface, we test all the permutation. Each permutation is also rotated in order to align their first point with the x-axis using the centroid as a reference. Then we can put the template on the top of each of these permutations, pair the different points, and compute the distance as the sum of the distance between the different pairs of points. This result distance is the smallest one, which is the one corresponding to the best alignment between the template and the input. At the end, our recognizer does this best alignment treatment for all the template and returns the template that gives the minimal distance. So touch tokens rely on a hypothesis that the geometry of the tokens impacts how user grasps them, and that our recognizer can discriminate the different resulting touch patterns. In order to test this hypothesis and identify a set of tokens that can actually be discriminated, we first run a formative study. The participants have to grasp a set of 12 tokens that vary in shape and size. We have 3 different types of interactions. In the first interaction, the participants have to select the right token and put it anywhere on the tabletop. They are not forced to adopt a specific grasp. They are just told to hold the token with at least 3 fingers for 1 second on the surface. In the second interaction, participants have to select the right token, put it in a specific location that is indicated with a black cross, and hold it with at least 3 fingers for 1 second. We consider 5 different locations. In the third interaction, participants must hold the token on a cross and then follow a path indicated by purple arrows while holding the token. We consider 6 different gesture paths in this interaction. And here are observations. On the graph, the x-axis represents the 12 different tokens, and the y-axis represents the recognition accuracy that our recognizer output. We collected 9 trials per token, following a per participant training. We use the first trial for training and the 6 others for testing. But we can see that the recognition accuracy range from around 50% to 75%. These recognition rates are too low to develop a robust system. To understand our results, we look in more detail at the different touch patterns that we have collected in our experiment. Our analysis revealed 2 sorts of confusion. First, there was some intergrasp variability. This comes from the fact that on a given token, one participant has a bit of variability in the location of his finger when he grasps the same token over time. Second, there was some intergrasp similarity. Actually, different users may have different strategies for grasping the same token. For example, we observed 3 different strategies for the square token, and also some strategies cause more confusion than another. For example, the third strategy for grasping a square token is very close to the second strategy for grasping a triangle. After this formative experiment, we have to find a way to reduce the variability that we observe in users' grasp. One way to do it is to control the user grasp by carving notches in order to indicate where the finger should be put. With this approach, we expect users to have a very consistent way to grasping a token, and we can even get rid of any training. Our recognizer will simply consider what we call a universal template. This universal template is a touch pattern for one token where each point is offset from 5 mm along the normal at the center of the notch. Here, you can see the set of tokens that we have designed and tested. We kept this specific shape and size as we were reported as the most comfortable by our participants in our previous experiment. And we ran a summative experiment with this new set of 6 tokens. The setup was similar to the one on the formative study, except that we ran the experiment on 2 types of capacity surface, tabletop and a tablet. And here are the new result we got. The recognition rate are very high with this new token design. For the tablet, it is 99% on average, and the tabletop it is 98, almost 99. And also I want to insist on the fact that our recognizer was not trained. It's relying only on a single universal template per token, and that universal template is exactly the same for all the users. So tangible interface have a lot of application domains that include data visualization, game, education, so on. As touch tokens do not require the use of a specific material for building the physical tokens, it offers a lot of flexibility for designing the right token depending on the target application. I will show a set of examples where we have used different materials. We develop a simple scatterplot visualization. The tokens are associated with the set of data points having the same shape and color. For example, user adjusts the visual representation of the corresponding data point in the scatterplot, changing the size by rotating the token or the opacity by sliding the token. Here, you can see touch token made of a transparent acrylic that acts as a physical magic lens. The tokens are associated with different layers. When the user places the token on the screen, the application shows the corresponding layer and an area below the token. Another example with transparent acrylic token, where user controls different game characters with different tokens. A token controls the location and orientation of the associated character. Finally, we can see wood tokens that are engraved with icons, where we control the access to some application on the tablet. The application icon is disabled. The user needs the token to be able to the right token pattern that will actually launch the application. This is a way to implement simple access control when sharing the tablet with family or friends. But touch token offer an easy way to build a tangible interface, but have a few limitations. For example, users have to touch the token and the surface at the same time, meaning that if the user removes his finger but leaves the token on the surface, the system doesn't know if the token is still on the surface or not. In our experiment, we have tested one set of 6 tokens. Now we want to explore how to make a designer able to create other token sets that feature custom shaped tokens. And finally, the current API only provides touch point information and the ID of the recognized token. This limited information makes difficult the implementation on some behavior that we have seen in our application. For example, we have approximated the location of the token as the centroid of the touch point, but this approximation will be encoded for some shape or when the users hold the token with only 2 fingers. We plan to implement a richer API for addressing these issues. To sum up, touch token can be used to build low-cost tangible interface. It does not require any knowledge in electronic or implementation of image processing technique. It only requires easy-to-make passive token, as a cutter, and a simple tactile surface, like a tablet. As touch token can be made of any non-conductive material, touch token offers a great flexibility for interface designers. As illustrated in our proof of concept application, token can be made of different materials such as wood, acrylic, and they can be of different color or even feature specific engravement. Touch token doesn't need any per-user training. It works with a unique universal template per token, and it is fast and robust. We make the touch token API publicly available to developers in both TUIO and Android. I will show a short video the overall process for building a tangible interface with touch token. First, they fabricate the token by simply downloading the PDF file that we propose and sending it as a print job to a laser cutter. Then they have to remove the token, obviously. And second, they simply download the API or in TUIO or Android. Finally, they test the token in both, in tabletop or tablet. And they use the the API to develop their own application. And thank you. I will be happy to take any question.
Hello, Rong Hao Liang from National China University. I really like your work. It's very elegant.
Thank you.
But I also wonder one question because users has to keep their own hand to keep their finger stick on the screen. I was wondering about the user experience. Do they feel any uncomfortable with that? Or?
No, actually, when we did the first experiment, when we have the token, and we experimented with 3 millimeters the token, but they don't like it, so we changed to 6 millimeters, and with that thickness, the people they didn't say anything about how to grab the token, and that's it.
Okay, and I also wondering about the design choice because you can also apply conductive coating to make footprint on the accurate point, and that make the token easier to grab, and users don't need to stick on both touchscreen and the token. So have you tried that kind of experiment?
Sorry.
Just to compare
Yeah.
the tokens, the touch tokens and the conductive token. Yeah, because you can also apply conductive.
Yeah, no, I know that. But we try to do that minimalistic.
Okay.
To use the people don't have to knowledge about how to build the token.
Yeah.
That is our approach. But
Okay.
we didn't compare how it works with the conductive material, and that's it.
Yeah, maybe your approach can be more organic because you can easily change the modality by changing fingers, right? Instead of the conductive.
Yeah, but
okay.
with the notch is really simple. Actually, we didn't say anything how they have to grab, and they automatically grab the token.
Okay,
with the
thank you.
notch. Welcome.
Any more questions? We have a few more minutes.
Hi, Daniel Verhami from FXPAL. Great work. I have a question for you about kind of tying this to previous work where the user did not hold any tokens. So you've used the system, I'm sure, for a while now. Do you feel like at this point you don't need the tokens anymore and you can just put your hand in the right shape and get everything done? Is there kind of a cross from novice to being an expert like yourself?
No, the problem is if you want to recognize the specific location, there is a variability and you cannot recreate that touch pattern without the token. So if you want to guide the user, you need a token physically because it's not cannot reproduce that pattern again and again.
I'll ask a question. Maybe I misinterpreted, but it looked like in your the templates that you had developed all had 3 fingers associated with them, and yet in the video there were several examples of people only using 2 fingers. I'm just wondering how that works. Did you have more multiple templates per token?
No, it's work with 2 fingers, but the problem, like I said, we have a limitation because when you remove one of the finger and you don't know exactly the center of the token, and you skip a little bit, there is an upside of the centroid. But yes, but you need at least to recognize the 3 finger, and you can remove one of them.
Oh, I see. You have to start with 3, but then you can take one. I got you.
You
Okay,
need to
that makes sense.
recognize with
Okay.
3 fingers.
And I know you said this is future work, but I'm just wondering if you could speculate about how many tokens, different types of tokens you could support, and what are the limitations that you'll run into?
Actually, I don't know if I can say that. We try to create an application that the user can create their own shape, like a Batman logo, whatever, and they can use where the finger should be put, and we have that, and they can create as much they want to. We need to know there is no conflict between the touch pattern. I hope I cannot do something wrong.
Okay. All right. Let's. Well, actually, before we think, I was told I need to only speak into the microphone because we're recording, so I will do that. I'd like to congratulate Raphael and his co-authors on receiving Best Paper honorable mention. So let's all thank Raphael and congratulate him.